the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students, specifically those who've already learned about vectors, vector equations, homogeneous systems, linear combinations, and pretty much everything else prior to that in linear algebra. In this video, we're going to talk about one of the most important concepts going forward in linear algebra. It's called linear independence, and we have its stepbrother, linear dependence. Both of them are important concepts. We'll start by defining linear independence, an indexed set of vectors. And what I mean by indexed set is that it's a set of vectors with subscript notation. It doesn't actually have to be subscript notation, but it's just a bunch of vectors, maybe 10 vectors or 27 vectors or something like that. But it's a set of vectors. And those vectors are in some space, Rn in this case. So each of them has n entries. Anyhow, that set of vectors is said to be linearly independent if the vector equation that you see right here, x sub 1 v sub 1 plus x sub 2 v sub 2 plus so on and so forth plus x sub p v sub p equals 0, that vector equation right there, only has the trivial solution. Now there's a lot of deep theory going on here, and there's a lot of definitions I can throw at you from the past right now, but for the moment, let's just go ahead and talk about what this implies. And in fact, I'll go ahead and start throwing some definitions at you from the past. We have a linear combination of the vectors v1 through vp. But this is a very special kind of linear combination. Normally, if I give you a linear combination, it's something like, oh, I need 3 times that first vector, minus 2 times the second vector, and so on and so forth down the line, maybe plus pi times the last vector, right? That would be one linear combination of that set of vectors. However, that's not what we're talking about here. These values, the weights that you see right here, again, bringing in definitions that we've introduced in the past, are all variable. We don't know what they are. They could take on many different values. But what we're saying in this definition is, no matter what value we try to plug in for x1, x2, all the way to xp, the only way to get that linear combination to turn into 0 is if x sub 1 equals x sub 2 equals x sub p equals 0. In other words, that all of those weights have to be 0. Now, does this mean that every time you're handed a linear combination of the vectors v1 through vp with variable coefficients, and I say that that equals 0, that implies all x1 through xp have to be 0? No. But if this set of vectors is going to be linearly independent, then the answer to that is yes. Again, there's so much to be said about this definition that I want to spend a little extra time here. And it's nice to bring in definitions you've recently learned. And so let's go ahead and bring in a definition that has been recently added to your vernacular, or the language that you use in this course. Recall that we had defined the span of a set of vectors to be the set of all possible linear combinations of those vectors. For example, if I said I had the span of the vectors v1 through vp, well, this linear combination right there is in that span because it is an actual linear combination of those vectors. And remember, the span is the set of all possible linear combinations. But another linear combination that's in that span of all those vectors is this. Another linear combination that's in the span of those vectors is this one, or this one, or this one. So you could probably tell right now, the span of these vectors v1 through vp is an infinitely large set of vectors. Now, why am I mentioning that here? It's because if you take a look at the left-hand side of this equation right here, the fact that these weights, x sub 1, x sub 2, all the way to x sub p, are variable, that means they could cover all the bases. In other words, this left-hand side could represent a massive number of linear combinations of those vectors. It may only represent one linear combination, but it could represent an infinite number of linear combinations. It just depends upon what combinations of x sub 1, x sub 2, x sub 3, all the way down to x sub p are required so that we force that left-hand side to become 0. So in a very real way, what we're saying when we say, does this have a solution? And of course, this does have a solution. The solution to this is always going to be at least the trivial solution. In other words, if we let x sub 1, x sub 2, all the way to x sub p be 0, that is one actual realistic solution. But we know from our work with matrices so far that there could actually be a lot more in the way of solutions. We can have an infinite number of solutions. I'll talk about that a little bit more in a minute. But asking this question right here, is there a solution to this, is basically the same as asking, is there a linear combination of those vectors that will become 0? Of course, we already know there is the 0 vector, but it's the same as asking, in the span of those vectors, which is a set of all linear combinations of those vectors, is there more than one linear combination, which by the way is a vector by itself, but is there more than one linear combination that turns that into 0? Now again, we know that the trivial solution will always solve that vector equation. And let me put it in very clean and clear terms. We know how to trade out a vector equation for a matrix equation. Remember, if we build a matrix whose columns are these vectors v sub 1, v sub 2, all the way to v sub p, and if we were to multiply that matrix by a column vector whose elements are x1, x2, all the way down to x sub p, we know by matrix vector multiplication that this product of this matrix and this vector will be this linear combination right here. So we're really asking, when we have the matrix vector product, which I'll call A times X, we're asking, is there a solution if we let that equal 0? Not only is there a solution, but is there a non-trivial solution? And again, we know this homogeneous equation, notice how I'm still bringing in more definitions from our recent work. Does this homogeneous equation have more than just the trivial solution? Remember, a homogeneous equation always has at least the trivial solution, x equals 0. But does this have more than that? Because if it doesn't, if it only has a trivial solution, then the columns of A, which are the vectors, v1, v2, all the way up to vp, must be, by definition, linearly independent. So this one definition brings together a lot of stuff that we've learned so far in linear algebra, and I'm spending a great deal of time on it because it's that important. Now let's take a look at the stepbrother to this definition. And that stepbrother is called linearly dependent, or linear dependence. So let's delve into this definition. Again, it starts with an indexed set of vectors, v sub 1 to v sub p in Rn, same kind of definition, but this set is said to be linearly dependent. And by the way, I didn't mention it in the previous page, but when I talk about linear dependence, I will use LD. And when I talk about linear independence, I will use LI. Just like when I talk about linear combinations, I would love to use LC. It's just faster for me to write, but because I'm producing videos, it's actually okay for me to write it out. I'm not in front of you in a class and taking time from you in a classroom. So for me to write it out and speed it up in the background, that's pretty okay. Anyhow, an index set of vectors is said to be linearly dependent if there happens to exist some weights, C1 through CP, not all of them being 0, such that this linear combination of those vectors turns into 0. Remember, linear independence told us that if these were variables here, x1, x2 to xp, and we set this linear combination to equal 0, the only solution should be the trivial solution. What's the opposite of the only solution being the trivial solution? The opposite of that is there must be at least one non-trivial solution. Let me actually write that down. All right, so the opposite of what we use for linear independence, I'll use Li right here above. The opposite of only having the trivial solution is having at least one non-trivial solution, and this will be for linear dependence. So again, looking at this linear combination, notice I didn't use x's there. The reason why I didn't use x's is because I only need one such set of weights, where not every single value in those weights is 0. There could be some that are 0, but not every single one. We don't want every single one of them to be 0 because that would be the trivial solution, and we don't want to work with the trivial solution. So we have to pretend as though one of these values, C1 through CP, is not 0 at least one of them. And we only need one combination of those that turns this linear combination of vectors into 0 to basically tell us that set of vectors is now linearly dependent. And looking at my note here, there was a little mistyping or misprinting there. That equation, that linear combination equaling 0, is called a linear dependence relation. I will actually not use that phrasing very often, if ever, in this course, but your instructor might. So that equation is called a linear dependence relation when not all the weights are 0. That is, when you have at least one or two of those weights being non-zero. A lot of them can be 0, but at least one or two non-zero is required. What I had written there kind of didn't say that exactly, so I had to fix it. So I really want to drive home the point. You have a set of vectors, v1, v2, all the way to vp. And notice I'm writing it as a set. It is actually a collection of vectors. What I'm going to do, because I prefer to do it this way, I'm going to create a matrix with those vectors as the columns. And I'm going to summarize linear independence and linear dependence right here. If the matrix equation AX equals 0, which is a homogeneous equation, only has the trivial solution, so no other solution but the trivial solution, then those vectors are linearly independent. If the homogeneous equation has more than the trivial solution, that's kind of an abuse of language right there. If it has the trivial solution and then more solutions that are non-trivial, then those vectors are linearly dependent. That's it. That's linear independence versus linear dependence of vectors. And that is hugely important. Let's actually see this in an example. Just introducing these definitions is really not enough. So let's jump forward to an example. Consider the vectors v1, v2, and v3 that you see right here. Are these vectors linearly independent? We'll answer that question first, and then we'll focus on the rest of the question. And I needed to kind of zoom out a little bit so you can see the rest of the question. If you want to read it, you can read it, but I'm actually going to focus on part A first. Now, those vectors are considered linearly independent if this vector equation right here only has a trivial solution. Another way of saying that is, if I consider all possible linear combinations of the vectors v1, v2, and v3, and the only linear combination that results in the 0 vector is the linear combination where the weights are all 0, then they're linearly independent. Another way I can say it is if I write this in matrix form, assuming that you and I both agree that the column vectors of A are v sub 1, v sub 2, and v sub 3, then those vectors are linearly independent if the only solution to this homogeneous equation is the trivial solution. Now, I'm going to really use a lot of language that we have developed within this course in this example. So let's go ahead and build a matrix equation here because, to be honest with you, that's what I like to do. Now, this will likely be the last time that I slowly transition from a vector equation to a matrix equation. The only reason why I'm being this slow with it is because we're kind of at the beginning of linear algebra, and there's a lot of stuff happening to you this early on in a linear algebra course, and it's nice for somebody to pause for a moment and say, well, let me step you through this process piece by piece. But we know that this is going to look like the columns v1, v2, and v3 augmented with 0, 0, 0. That's the matrix equation written as an augmented matrix. I actually did kind of speed up a little bit, but you should know at this point that you can transition between vector equation to augmented matrix that quickly, or from a linear system to an augmented matrix that quickly, or from a matrix equation to the augmented matrix that quickly. We want to find a solution to that matrix equation, and by doing row reduction on this augmented matrix, we should hopefully find a solution. Now, if this augmented matrix looks familiar to you, it's because it was in a previous lecture. Notice right here, we have the same augmented matrix, 1, 2, 3, 4, 5, 6, 6, 7, 8. That's the coefficient matrix, and the augmentation column is all zeros. And when we went through and did all the row reduction methods, we got down to this row reduced form of the augmented matrix. This is row equivalent to the original matrix. So what I'm going to do is move that result over. If you need to figure out how we got there, watch the previous video. I don't know which video this is, but it's within the last maybe 5 or 6 videos. So I just copied it and moved it over here. So this is these two augmented matrices are row equivalent, which means their underlying matrix equations have the same solution set. Now, if you take a look at this, we have a pivot in column 1 and a pivot in column 2, but no pivot in column 3. We also have a theorem that tells us if we don't have a pivot in the rightmost column of an augmented matrix, our system is consistent. Well, we knew this system was going to be consistent because it represents a homogeneous equation. So I really didn't need to mention that, but we have another theorem. It's actually the same theorem. It's called Theorem 2, at least in the textbook that I use, that tells us if you have any free variables, and here we have a column without a pivot, so we do have free variables, then your system has an infinite number of solutions. Again, that's only if your system's consistent, and the system is consistent. So it's consistent, it has a free variable, therefore there are an infinite number of solutions. That is, our original matrix, which is up here, has more than one solution. Well, we know one solution is a trivial solution, but this has more than the trivial solution. Since it has more than the trivial solution, the column vectors that built that matrix must not be linearly independent. I'm going to write that down and give the reasoning. So are these vectors linearly independent? No, because the matrix representation shows a non-pivot column in the coefficient matrix, and this implies a free variable in the underlying linear system. Thus, AX equals 0 has an infinite number of solutions. Well, we weren't working with AX equals 0 initially. We built that from the linear combination of the vectors v1 through v3. Hence, the vector equation x sub 1 v sub 1 plus x sub 2 v sub 2 plus x sub 3 v sub 3 equals 0 has infinite solutions. And so basically infinite solutions, one of them is the trivial, but the rest are non-trivial solutions. Now, I was pretty wordy with that, but I really want you to get this concept. So that's why I'm taking my time. Part B says, if possible, find a linear dependence relation. There's that word or that phrase. And I told you that I wasn't going to use that phrase if ever, but here I'm using it right here, but probably the last time I'm going to use it, honestly. If possible, find a linear dependence relation among these vectors. Now let's remind ourselves what a linear dependence relation is. Equation 1 in the definition of linear dependence is called a linear dependence relation. It's basically saying I have a linear combination of our vectors that will become 0, where that linear combination does not have all 0 weights. So there must at least be one non-zero weight in C1, C2, all the way to C sub P. The question is, can we do that here? Can we build a linear dependence relation here? And the answer is yes. What we're going to do is go ahead and take our final reduced row echelon form augmented matrix here, and that's kind of what you need to get it to, is a reduced row echelon form, so that you can write out the relationships between x1, x2, and x3, the weights on these vectors. Remember, this first column right here is the vector v sub 1, this is v sub 2, and that's a vector v sub 3. What we're trying to do is find the weights x sub 1, x sub 2, and x sub 3 that are required to force the linear combination of those vectors to become 0. And when we solve this matrix equation using row reduction techniques, specifically I went down to reduced row echelon form here, we will get some type of relation between x1, x2, and x3 that will tell us those weights. So let's see what this is. We have x sub 1 is equal to x sub 3, x sub 2 is negative 2, x sub 3, and x sub 3, because, well, it's in a non-pivot column, it's a free variable. We're allowed to choose whatever we want. Now there are an infinite number of linear dependence relations here, but one such linear dependence relation for this set of vectors v1, v2, and v3 is going to be if we let, for example, x3 be 1. Just try that. Let x3 equal 1. Then one linear dependence relation is x1 being 1 times v1 minus 2 times 1 times v2 plus x sub 3, which is 1 v3. That should turn into the vector 0. Now you can actually test that, by the way. Take 1 times this first vector, subtract twice that second vector, and add one of these. 1, negative 2, 1. Okay, let's try that. That would be 1 minus 4, which would be negative 3, plus 3. That is 0. Well, let's try it in the next row. One of these, that's 4, minus 2 of these, so 4 minus 10 is negative 6, and add one of those. Negative 6 plus 6, yep, that's 0. And we could try it again in the last row if you want to, if you're not convinced, right? One of these, that's 6, minus 2 of these, so 6 minus 14 is negative 8, and one of these plus 8 is definitely 0. So it is true that this specific linear combination, where notice the weights are not 0. It's not 0v1, 0v2, and 0v3. It's actually non-zero weights there, and that still turns into the 0 vector. So these vectors are linearly dependent because we found a non-zero set of weights that will turn that linear combination into 0. That's not the only linear dependence relation. Another linear dependence relation occurs if we let x sub 3 equal negative 5, for example. Well, I go up there, x1 is just x sub 3, so we have negative 5 v1. X sub 2 is negative 2 times x sub 3, so negative 2 times negative 5 is positive 10 v sub 2. And then finally, x sub 3, well, that is x sub 3, that's just negative 5, so minus 5 v sub 3. And if you do what we did over here with those new numbers, which I'm not going to write in, but if you do that, again, do all that work, you'll find out those rows do turn into 0. So that's yet another linear dependence relation. Now, something I want to warn you about, and you probably already read this, because it's been in your field of view here the entire time. Whenever you study a homogeneous equation, which is basically what we're going to be doing when you deal with linear independence or linear dependence, you may be tempted to omit the augmented column of zeros when you're doing your row reduction techniques, because that augmented column of zeros, well, it never changes. It's always zero, right? There's zeros, started with zeros. You could be very tempted to not write that column of zeros. However, I urge you to keep the column of zeros, mainly because leaving them out sometimes leads to misinterpreting your calculations. So it's just safe to leave them in. It's just a simple single column of zeros. It's not that big of a deal to leave them in. All right, I know this video is exceedingly long for such a short sounding topic, but it's this important. You must be awesome with this to be good in linear algebra. Luckily, if you just hop back to my summary right here, that pretty much is it. You know that you have a set of linearly independent vectors if AX equals 0, where A is just a matrix of those column vectors, only has a trivial solution. Otherwise, if it doesn't only have the trivial solution, they're linearly dependent. That's an easy way to remember that. Super succinct. All right, I am done. You guys have a wonderful day. Good luck in linear algebra. Be wonderful people.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.